Hello, today we're going to be looking at continuous random variables. Now in this first video I'm just going to remind you of a couple of things that hopefully will be helpful to you as you work through these new types of problems. Up to this point, most of what we've done has been discrete random variables, where the random variable had to be a counting number, right? We had 1 success, 2 successes, we had 3 pens, whatever it was, we ended up with whole numbers. Counting numbers. In this situation, we're now moving on to continuous. We've done a little bit of that before with the normal distribution, where we were allowed to say, well, the value doesn't have to be a counting number, it can be any of the decimals in between, meaning an infinite possibility. Now that means that for one specific value, the chances of that specific value are infinitely small, but over a range we could add up and have several have a finite probability for a range of values. So I just want to do an example to kind of remind you. Let's consider f of x equals kx. Okay, so just a straight line, y-intercept of 0, slope of k, and this function is a PDF, a probability distribution function for x between 0 and 6. Now what does that mean, that it's a probability distribution function? Well, if it's a probability distribution function, then the sum of all the probabilities is 1. Now we got a problem here in that the probabilities are infinitely small, and there's an infinite number of them because x can be anything, not just whole numbers. And so instead of using this summation, what we're going to use is the integral. So we're going to say the integral from 0 to 6 of f of x dx must then equal 1. And so when I do that, I just go integral from 0 to 6, and f of x, of course, is just kx equals 1. I pull the k out and do the integral. So x squared, then put the 1/2 in front, from 0 to 6. If you don't remember how to do that, you probably need to go back and look at your integrals, and of course still equal to 1. Now I evaluate from 0 to 6. If I put 6 in, 6 squared is 36 times 1/2 is 18, minus, if I put 0 in, I get 0, so k times 18 minus 0 squared is 0 times 1/2 is 0 equals 1. 18 minus 0 is 18, divide by the 18, and k, of course, then is 1 over 18. So when k equals 1 over 18, I've got a probability distribution function. All right. Now, what if, say, I wanted to know the 90th percentile of this probability distribution function? For what value is above 90% of all the other data? Okay, so well, let's think about this. If I got a graph here, and here's my function going from 0 up to 6, at some point you've got 90% of your data, right? Remember, the whole triangle is 100% of your data, and somewhere here we get 90%. All right, so if everything adds up to 1, then 90% would be 0.9. So this area right here needs to be 0.9. And so what we're going to do is we're going to find the integral. Actually, we don't need to find the integral because it's a triangle. I could do an integral, but it's a triangle, so I don't need to worry about that. So I just do length, which is x, times the height, base times height. The height, of course, is just the y value there, and so that would be 1 over 18x. And then, of course, because it's a triangle, it needs to be 1/2 base times height, and I want that then to be equal to 0.9. And so from there I can solve. I got 1 over 36x squared equals 0.9. And I can solve that using a fancy schmancy calculator such as this one. So I go 0.9 times 36 and then square root it, and I get 5.69. Which makes sense because that's up near the top end of my rectangle, so most of the data is below that. So 5.69 then would be considered the 90th percentile. Okay, so that's just a reminder, a couple of reminders. Please do also remember a couple of other things that we've done. Please remember that the expected value of x or the average, is simply the integral of x f of x dx, for the same reason as what we were talking about in the past, where we were just using the summation. It's just a finite, infinite summation of that then. And then you've also got the variance of x, which we had many different ways of doing that, but you can do it as an integral, and the integral could be x minus mu squared f of x dx. And that's given to you. It's given in many other formats, but generally we look at it as e of x minus mu squared, or the expected value of x squared minus mu squared. And so all of these will be things that will be useful as we go through the next little bit. Alright, so that's your first video, just a couple of reminders, and go on to the next one, and we'll start looking at a couple of different formats.